I will talk about a couple of different kinds of regression graphics, in particular added variable and component plus residual plots. Because this is a conference about software, I'm going to focus on the implementation of these methods, including various extensions, some of them quite recent, in the CAR and effects package in R. And as I've been listening to the other talks, I realized that this talk might be something of an outlier in several respects. One is that the basic methods that I'm going to talk about, not necessarily the extensions, are really quite old. And as well, the basic implementations, or the original implementations in the CAR package, at least, are also quite old. I looked today and I discovered that the CAR package was initially contributed to CRAN in 2001. Of course, it's been substantially developed since. And the effects package initially contributed in 2003, although the addition of component plus residual plots, or their integration with the effects package, is quite recent. So after a brief introduction, I'll first talk, and relatively briefly, I hope, about added variable plots. My talk will primarily be a demonstration, so I'll try to move fairly quickly through my slides, particularly the more theoretical ones. I don't see a way, or I'm not aware of a way of posting conference slides and other materials to a conference website. So I'll instead put these on my website sometime in the next couple of days. And I've just added the URL of my home page to the chat. Okay. So as I mentioned, I'm going to talk about two kinds of regression graphs. These are really diagnostic plots for regression analysis to try to figure out whether a regression model that we fit to the data adequately represent the data. The implementation is in a number of functions in the CAR and effects package. I've listed some of the principal ones here, but there are also related functions in these packages as well. And for purposes of the talk, I'm going to focus on linear least squares regression, mostly for simplicity, and because the method is basic to these kinds of regression graphics. But both added variable and component plus residual plots can be extended to other classes of regression models, including but not limited to generalized linear models. And these methods, many of them anyway, are also implemented in the CAR and effects packages, and some of them in other packages that I've been involved with as well. And I should mention at the outset that a lot of what I'm going to describe was work that I've undertaken along with Sandy Weisberg at the University of Minnesota, or I should say, like me, retired from the University of Minnesota. At the end of my slides, I have a number of references, and here are the general and key ones that cover largely what I'm going to talk about today. So for added variable plots, I'm going to concentrate on the definition so we understand what we're going to be looking at, and try to move relatively quickly to a demonstration. An added variable plot, it's also called a partial regression plot, but I prefer the term added variable plot because it's easy to confuse partial regression plots with other kinds of regression graphs. An added variable plot is primarily useful for examining influence, and that is an unusual data in regression analysis. And in least squares regression, the construction of a partial regression plot or added variable plot is very simple. Okay, first, we take the response variable in the regression, and we're going to focus on a particular regressor in the model, maybe an explanatory variable, or it may be one regressor in a term, such as a polynomial regressor or a regression spline regressor or an interaction regressor. We're going to focus on one regressor in the model and its coefficient, let's say, without loss of generality, x1, and regress the response variable on all of the other regressors in the model, obtaining residuals, which I've denoted here as y super 1. And then we're going to take the focal regressor x1 and do the same thing, that is, regress it on all of the other regressors in the model, obtaining residuals, which I've denoted x super 1. And then the partial regression plot, the added variable plot, is simply a plot of the residuals for y on the vertical axis versus the residuals for x1 on the horizontal axis. And the spirit of this is we would draw one such plot for each regressor in the model, including possibly, though not necessarily, the constant regressor x0. So we would repeat this for each of the regressors in the model. And in effect, what we would have done is reduce the k+1 dimensional point cloud of the data into a series of two-dimensional graphs. So the object is to visualize leverage and influence on each of the regression coefficients in turn. And added variable plots have a number of interesting properties, which are both pedagogically interesting and also useful for this task, that is, of visualizing influence in regression. Okay, I'll leave this to you to read. Okay, it's also possible to extend added variable plots to two regressors, that is, to a series of 3D graphs. And we proceed in a similar manner, except that we regress each of two regressors, x1 and x2, along with y on all of the other regressors in the model, obtain residuals for all three, and draw a 3D scatter plot of the resulting residuals, with x1 and x2 on the horizontal axes of the plot and the y residuals on the vertical axis. And the properties of the resulting graph are essentially the same as the properties of 2D added variable plots. Okay, so here I'm using RStudio. I actually thought about whether to make this talk into a notebook rather than a script with a set of associated slides, and decided to stick with the simplicity of a script. I'll begin by loading the CAR package, both for functions and data sets. I'll use a particular data set, which is in the CAR data package, which loads along with CAR. The data set, without getting into tremendous detail, was the original data set that was used to calibrate the first substitute occupational prestige scale. The data are for the US around 1950. The three variables that we'll be looking at initially for each of 45 occupations, these data were collected and analyzed by the sociologist Otis Dudley Duncan, are the income and education levels of the occupations thought of as predictors of prestige, and the measured prestige of the occupations. Income and education came from the US Census. Prestige came from a survey of the US population. Okay, so to get a quick view of the data, I'll use the scatter plot matrix function in the CAR package, and without belaboring the graph with which you're probably familiar, on the diagonal, I have the univariate distribution of each of the three variables, the predictors, income, education, and prestige. Sorry, the predictors, income, and education, and the response, prestige. And off the main diagonal, I have pairwise scatter plots. So in the last row of the plot, prestige is on the vertical axis, and each predictor, income and education, on the horizontal axis. And the way I've created this scatter plot matrix, according to a certain rule based on Mahalanobis distance from the centroid of the scatter plot of the panel, I've noted the three most unusual cases. And we'll notice that if we look at the scatter plot of income versus education, we can see that three occupations stand out. Ministers who have relatively low income given their relatively high level of education, and railroad engineers and railroad conductors who have relatively high income given their relatively low level of education. None of these cases are univariate outliers, but they are bivariately unusual. And because this is the space of the predictors, these observations are going to have substantial leverage on Duncan's regression. This is the model that Duncan fit, a model that he used to produce prestige scores for several hundred other occupations for which he had income and education levels in the census, but not prestige scores. And if we, that is a linear regression of prestige on income and education. And if we summarize the model, we can see an impressive R squared of 0.83, coefficients that are many times their standard error. So superficially, at least, if we don't look further, we, as Duncan was, would be relatively happy with this regression. To create added variable plots for the data, I use the AV plots function in the CAR package. Method equals identify means that I can identify points interactively with the mouse. And in the RStudio graphics device, this means I can click near a point, but the point label won't show immediately until I exit from identification mode. So there's the first added variable plot for income, and the second one for education. Again, I'm going to identify the points that seem noteworthy. And let's zoom that plot so that we can look at it a little bit more clearly. So here in the added variable plots, we see how these three unusual cases affect or don't affect the regression coefficients. Conductors pull the income coefficient down at the right, while ministers simultaneously pull up at the left. These cases are a widely separated influential pair that make the income coefficient smaller than it would otherwise be. Railroad engineers are at a very high leverage point, given their unusual income, given their education, but they are more or less in line with the trend through the data. The plot for education is very similar, except the effect is opposite, Ministers are pulling up at the right, conductors down at the left, consequently making the education coefficient larger than it would otherwise be. Okay. I'm trying to, there we go. Close that zoomed view and update the model, removing ministers and conductors and comparing the coefficients between the two fits. And we can see that just removing those two cases, the income coefficient, as we would expect, based on the added variable plot, is much larger than it was before, and the education coefficient considerably smaller. Okay, we're going to look at a 3D version of this plot, but it's not all that interesting here, because what it does is, in effect, reproduce the three-dimensional scatter plot of the data. The CAR package uses the RGL package for 3D graphs. That's due to Duncan Murdoch. And I don't have to, but I'm going to open an RGL device just so I can get it the size that I want initially. And then use AVplot 3D to make the 3D added variable plot of the data and to rotate it automatically along the horizontal axes so that we could get a look at it. And I've also identified the three most noteworthy points, which unsurprisingly are ministers, railroad engineers, and conductors. And we can see how the fitted regression plane is influenced by particularly conductors and ministers. Okay, so those are added variable plots, at least as applied in least squares regression. And let's talk about component plus residual plots. I'm going to talk about what these plots are good for, in particular for detecting nonlinearity in the broad sense of lack of fit. Explain very quickly why marginal plots and residual plots of the data are not really adequate to the task. I'll define what a component plus residual plot is, and the rest I'll probably leave for you to read at your leisure. Okay, so the assumption in the standard linear regression model that the average error is zero everywhere implies that the regression surface that we fit to the data, whether it's a flat surface or a surface that might have curvature in it, due to the use, for example, of polynomial or regression spline terms or interactions, that captures the systematic dependency of y on the axis. So that violating the assumption of linearity is the same as saying that the model doesn't capture the way in which the average response changes with the explanatory variables. Okay, so if we specify that a relationship is linear and it's actually nonlinear, that would be a violation of the assumption of linearity. But so would an interaction if we've specified that the model is additive. Okay. Component plus residual plots are useful for diagnosing nonlinearity, and the extensions of these plots that I'm going to show you are useful for diagnosing nonlinearity in the more general sense of lack of fit. The problem that we're facing is, in a sense, similar to the problem that added variable plots speak to, which is that the regression surface is high dimensional In general, if we have P predictors, it's a P-dimensional surface in a P+1 dimensional space. I no longer want to equate explanatory variables with regressors, because in linear models, often or even typically, there are explanatory variables that could give rise to several regressors, or regressors that are functions of more than one explanatory variable. Here, in constructing a component plus residual plot, though, my focus will be on the explanatory variables, not necessarily the regressors. Although for initial simplicity of exposition, I'll equate the two. So there's a similarity between added variable and component plus residual plots, but they're constructed differently and they serve different purposes. As in the case of added variable plots, we can extend component plus residual plots to 3 dimensions, and it's actually potentially useful to do that, for example, to detect interactions. Okay, so here is a very simple motivating example that shows why simple scatter plots of the data or plots of residuals may be inadequate. And I've taken a case, well, first of all, plotting y against each x can be inadequate if there's more than one x, because we're interested in the partial relationship of y to each x controlling for the other x's when we do a multiple regression. Okay. Second, plotting residuals against each x can detect nonlinearity, but it doesn't show us the kind of nonlinearity. So I've illustrated that here with 2 simple 2D scatter plots, which are at the top in panels A and B. In scatter plot A, there's a nonlinear but monotone relationship of y to x, while in scatter plot B, there's a curvilinear, that is a non-monotone relationship between y and x. If I take residuals from the least squares line in each of these scatter plots and plot the residuals E versus x for each of these cases, like the way I've constructed the example, I get exactly the same plots. So I'm unable to distinguish case A from case B from the residual plots against the x's. Now, why would it be important to do that? Well, because I would model these relationships differently. In the first case, for example, I might be able to transform x, say, by using x squared in place of x, to straighten the relationship of y to x. While in the second case, I might use a quadratic, that is both x and x squared in the model. With more complex patterns, I might use a regression spline. Okay. Let me shift gears and go back to the examples. Okay, I'm going to load a data set, which is on my website, which is data from the CIA casebook, where the cases are countries. And the variables here are GDP per capita, infant mortality rate per 1,000, that is, infant deaths per 1,000 live births, the Gini coefficient of income inequality in the country, ranging from 0, perfect equality, to 100, perfect inequality, and per capita health expenditures in thousands of US dollars. And without much motivation, let me regress the log of infant mortality on GDP per capita health expenditures, and the Gini index of inequality, and summarize the resulting model. You can see I have a respectable R squared of 0.71 and coefficients that are not necessarily many times their standard errors, but at least a couple of times their standard errors. And let's start with conventional component plus residual plots for that model. By the way, I logged the response because infant mortality across countries is very positively skewed, making it not a very promising response variable in a least squares regression. So apparently, the partial relationship of log infant mortality to GDP per capita is nonlinear. The magenta line represents a smooth through the component plus residual plot, while the broken line, in effect, represents the regression surface viewed at dawn. Its slope is the slope of the GDP coefficient in the multiple regression. In contrast, there seems to be an uncaptured curvilinear or what looks like quadratic relationship between infant mortality and health expenditures, holding GDP and Gini coefficient constant, and the partial relationship of log infant mortality to the Gini coefficient seems to be reasonably linear. So we could try refitting a model in which I log GDP to straighten this relationship, fit a quadratic in health expenditures, and leave the Gini coefficient as a linear effect. I have here an ANOVA table for the resulting model. You can see, by the way, that the R squared is much larger than for the previous model. Here is an alternative version of that plot, plotting in a slightly different way. In the previous version, a traditional component plus residual plot, I'm plotting against in the original predictors. Whoops. Here, actually, sorry, I never showed you this. Here we, yes, sorry, I've backed up, and here are the component plus residual plots for the respecified model. So what I'm plotting against are regressors. So if I've adequately fixed the model, these plots should look linear, and they do. In the case of a 2 degree of freedom effect, like the health quadratic effect, I'm plotting against the partial linear predictor. And if the relationship is really quadratic, that plot should look straight. An alternative way of doing this is what the effect package does. It puts the natural explanatory variables on the horizontal axis and plots partial residuals, that is component plus residuals, against the natural predictors, so that in this case, the blue curve represents the partial fit. So what happens when we log GDP or use a quadratic in health expenditures? And here we're to compare the magenta smooth to the blue fitted model. Okay. I've almost used up my time. So I'm going to show you one more thing. Can I take a few more minutes, like 3 or 4 minutes?
Of course.
Okay, yeah, not of course. I should be careful with time, but I'm going to artificially create some data. I have here what I'm thinking of as 3 explanatory variables, which I've generated as multivariate normal with a covariance matrix that is essentially a correlation matrix, where each pair of x's is moderately correlated, 0.5. And the variances are all set equal to 1. So it's not necessary, but these are standardized variables. And then defining a y variable initially according to a linear model with an intercept of 10, slope coefficients of 1, 2, and 1, and an error standard deviation of 3. Essentially arbitrary to create a neat example. And if I fit that model, I'll be fitting a correct model to the data. So if I look at a 3D component plus residual plot for that model, it should the 3-dimensional smooth, which is the magenta surface, should be close to the blue plane, which represents the fitted model. And indeed, it is. So suppose I create some data where, in fact, there's interaction. Okay, so I've defined a new response variable. I've called it y2, which is the same as the previous one, where the relationships were linear, but now add an interaction that is just a multiplicative interaction between x1 and x2 with a coefficient of 3. And if I fit the correct model to the data, you can see the regression coefficients are reasonably well recovered in this sample of 300. But I might also fit an incorrect model, say a linear model omitting the interaction. Okay, so what happens if we look at 3D component plus residual plots for the correct model? So once again, the fitted surface is the blue surface, and the smooth through the data, the 3-dimensional smooth, is the magenta surface. And where there are actually data, the two surfaces are very similar. And so that was the correct model, which included the interaction. What happens if I look at the 3D component plus residual plot for the wrong model? Okay. Very clear that the surface I fit to the data is different from the trend through the data. That is the average partial y value as a function of x1 and x2. Okay, so the lack of fit is well captured by the 3D component plus residual plot. Okay, now in this case, 2D component plus residual plots won't be informative. If I look at 2D plots for the, just backing up slightly, if I do look at 2D component plus residual plots for the incorrect model, I can see that something is wrong, but I don't see that what's wrong is an omitted interaction between x1 and x2. On the other hand, the component plus residual plots implemented in the effects package can draw effects and partial residuals, that is component plus residuals, of arbitrary complexity. So here I fit the correct model to the data, and here the incorrect model. In each panel, X1 is on the horizontal axis, X2 is fixed at a value across its range, small, intermediate, larger, and largest. And I compare the fit of the model, which is the blue curve, the same in all panels because there's no interaction in this incorrect model, with the trend through the data, which shows initially a negative slope, flattening out, becoming positive, and more positive as X2 increases. In other words, an interaction between X1 and X2. Okay, and I think I will leave it here. I have here some more theory of component plus residual plots and a bunch of references that greatly elaborate what I had to say.